Hi there, my name is Dominic Orchard. I'm a computer scientist here in the UK, and I've made this video because I'm advertising for a postdoc position at the moment to work with me for the next 3 years roughly at the University of Kent, and I thought it would be useful to just give a little bit more context to the job and some ideas about what I'd like to work on with this position. So if we haven't met before, just a little bit about me. As I said, I work in the UK. I actually work at two institutions. I work both at the University of Cambridge and at the University of Kent. My background is in programming languages. I've worked for a long time at sort of the intersection of logic, semantics and types, and I like to combine theory and practice together. So I like doing theory, but I also like to make things and apply that theory and think about how I can bring these ideas to ensure the correctness and good performance and expressivity of languages. Some people know me for the Granule project, which I've worked on for a long time. That's using the idea of graded modal types to add fine-grained reasoning into programming. But some people know me for my work with climate modelers and climate scientists, which I've been doing for some time. And one of my activities is co-directing the Institute of Computing for Climate Science, where I do a lot of that work, and I work closely with various earth scientists and climate scientists and looking at how we can support their work through the latest in programming languages and software engineering. So this particular postdoc job is related to those activities. It's really going to be about programming languages for climate science, for climate modelling. That's my vision for this role. It's going to be based at the University of Kent, but with then option to work with people at ICCS. So just a little bit of background. I'm sure you're all aware that, of course, the world is warming, and this nice graphic here represents that change above the average across the last 150, 170 years or so, which is quite a stark picture, of course. And while we've seen that warming increase, we know that our anthropogenic emissions of CO2 and methane and other things has gone up really exponentially, essentially. And through the fantastic work of scientists worldwide, we've been able to unpick, is the warming that we're seeing something that's just sort of inherent to the cycles of the Earth and the atmosphere, or is it caused by our activities? And I love this graphic because it contains so much of human knowledge and computation and modeling into a single graphic that shows that the observed warming that we're seeing, that's this sort of jagged black line, matches the aggregate of all of our simulations if you include the human factors and the natural factors of anthropogenic emissions and so on. And so that tracks very closely. And if we run those simulations without the forcings from human activities, then we get nowhere near as much warming. But that's still including all of the natural potential sources of warming and changes. So we've understood for some time that the climate change that we're seeing is due to our own activities. And there's a huge amount of very interesting science behind this, and of course computing as well, because climate science is a heavily computational field and it always has been, and it relies on building these amazing pieces of software to simulate huge numbers of processes in our atmosphere, oceans, cryosphere, biosphere, to understand how our world works and how we are changing it. So the modern climate models comprise of something called a global circulation model, which is, as I said, this really interesting piece of computation. We've got large amounts of spatial data structures and solving partial differential equations, doing approximations of those to get the fluid dynamics in the ocean and the atmosphere, and then bringing in models below our minimum resolution of resolving our flows of all other processes that exist at those levels and all the interactions between them. So they're really interesting pieces of computation, and they take a lot of work, many decades in the case of the large models that go into things like the IPCC report and the graphics on the previous slide. Now, there's a very nice book that I read a couple of years ago, last year, and has this really nice quote in it that I think kind of sums up a bit of the way I've been thinking recently. It says that our appreciation of the risks of climate change is limited by the way our academic institutions encourage each researcher to focus on their own narrow area of expertise. Now, many of you, well, some people might know me from my work in programming languages, and I worked in that for a long time, but about 10 years or so, or perhaps more ago, I was thinking, well, how can we take the ideas we've got in programming languages around verification and performance and languages to support programming, all of these things, and actually put them into the hands of scientists and actually listen to scientists and find out what they need and what the problems are and what the challenges are, and actually try and work with them. And that's something I've been trying to do for a while, and it's something I've been able to have funding to do more and more in the recent years. So what do we want to do in this space? We want to get better predictions. We want to understand how our world works with higher and higher fidelity. So really want to kind of climb this ladder of including more and more processes into our models and higher resolutions, so that we can have these models that let us really test lots of different scenarios at high resolution, bring in observational data, do data assimilation, predict at multiple scales with uncertainty, and also be able to then use that for risk assessment. So I think that challenge of sort of scaling up through the resolutions, and that the highest resolution models now are kind of at that 1 to 5K kind of resolution for their grid cells. And we're getting more and more processes in, trying to get more of the biosphere in as well, land surface models, chemistry as well, which is very expensive to compute, bringing in more and more of these ideas, and that's a scaling problem. And it's a scaling problem for computation. We have to do more and more computation to do this. But I think there are other kind of levels of scaling that are required here. We need to scale up our collaborations, lots of different scientific teams working together, and then scale up the communication between the teams and between us and the computer. And of course, that's where programming languages come in. So really, I really want to have more of this interaction between climate scientists who are writing code as a core part of their day job and programming language researchers. And I'm lucky to be able to work with lots of amazing climate scientists around the world, and it's just been really interesting to see everything they're doing and see their problems and work with them on some of these things, and then bring those ideas back to the lab and think about, okay, well, what's the programming languages that we need in 5, 10, 20 years to help this kind of work. So this is something I started, as I said, about a decade ago. I wrote this paper with Andy Rice, a computational science agenda for programming language research, where we kind of laid out some of the difficulties in modern science with using programming for modeling and having your model be code. And we talked about the need for more of this computer science engagement with scientists. We threw out a bunch of ideas about new ways of doing abstraction and specification that could help science. And then we advocated for sort of an evolutionary approach, where we build tools that can help people now in the programming languages and environments they're used to, sort of gradually bring them along with these tools, but also think about, well, what could future languages look like, and what features could we add to support computational science, and in this case, climate science, in the future. And so, I don't think that we're done with languages. We're not going to just say, okay, we've got Fortran and we've got Python 3.12 or 3.14 or whatever, and C++, and that's all everyone needs for the rest of time. I think programming languages can be extremely powerful tool for improving our ways of solving problems and solving them better. So we should look for how we can leverage languages in the future to aid in scientific domains such as this. So just a few kind of things, I've talked about this elsewhere, but a few kind of problems in this space to deal with. One of these is the semantic gap. People write papers with some kind of abstract modeling using mathematics, using some differential equations, but it's necessarily kind of a high level view. And then you do some numerical analysis, you discretize, you come up with some discrete approximation to those, and then build a piece of code that then actually does predictions based on that model, based on that discretization. And so you've got this code over here on one side and the abstract model in the paper on the other, and they become disconnected. There's a semantic gap between the two, and it can be very difficult to connect them, even if you've got both of them available. So I try and understand, well, how do these two things relate, and how can we understand this abstract model and its implementation side by side? And that's because there's really this semantic gap. They become disconnected. The code often, our languages don't do a good job at letting us bring in information from the domain into the language. So I think that languages should enable better domain description, and that could be something that could be worked on, for example, in this position. Another problem is having verification tools that are accessible and appropriate to the domain that can help people ensure the correctness of the software. Now, that might not be full formal verification things like we might see with SEL4 or CompCert or things like that, but gradual tools that help us squeeze out bugs, improve, speed up development processes, reduce the amount of time to get something that works and have confidence in it going forwards. So I think static analysis tools are a great thing that could be applied there, and it's something that we've worked on in various projects in the past. They're easy to deploy, you can deploy them more easily alongside existing processes. And with the right interface and training, they can be a big win, but they haven't really taken off in this field yet. So there's more work to be done. There needs to be more targeted analysis to help the scientists. So that could be, we've tried a lot of things before, and I'll mention those in a moment, but there's other things we could look at, like sensitivity analysis or robustness analysis to understand sort of numerical characteristics of the models, doing things like conservation analysis, like does the amount of energy or the amount of water in this system get conserved, or is there some bugs or some kind of numerical analysis problems, which means we're not getting that conservation. And can we look at domain-specific languages with correct by construction properties and leverage the kind of ideas from compositional correctness and build DSLs for people which have these things for free. So in a previous project I had, which is it's still going really, is that known as the CAMFORT project, we built some Fortran static analysis pipeline and some verification tools on top of it for scientists, one of which was a units of measure typing system which has polymorphism, type inference, it's sort of gradual, so you can add it a bit of a time, and you can also have it automatically generate specifications for you as well. So here's a little example, some Fortran code with these comments in, which are structured comments, which are our units of measure typing. And notice we haven't had to annotate everything in the program. We can run that through the CAMFORT tool and it says, yeah, everything, it does dimensional analysis and checks that everything is consistent. So we're still in the process of working how to scale that up to larger pieces of code and climate models at the moment. So that's ongoing work there about doing this at scale. And then from that work, we worked with the Met Office. We built a load of other static analysis checks for them to run on the unified weather and climate model that they have. And so that was running for a time at the Met Office to check the correctness of their code with sort of kind of linting style checks based on their internal style guide. So there's other things that could be built on top of CAMFORT. We've got a really nice sort of solid pipeline there with which more tools could be built and deployed with scientists. I think another problem is having interactivity at scale. And when I say interactivity here, I mean like interactive kind of programming. Notebooks are really popular in science, these kind of tangle and weave like environments where you write code, evaluate it, see the result, write some more code, see the result, things like that. But having that work at scale with then a piece of software that's modular and reusable and can be plugged into other things, there's a bit of a tension there. And often the sort of notebook style leads to things which are not very reusable by default. But the good thing about these kind of interactive systems is that they aid exploration. They can help with explanation, but I think our languages can assist with that as well. There are language ideas around about provenance tracking and transparency that can help with auditability of systems. And then I think we also want to bring in program synthesis as well to help people write code more easily by leveraging synthesis tools, having that interactivity where the human and the computer are writing the program together. So I think one of the things that I believe here is that we should be thinking about programming systems, not just languages. You know, languages in the traditional sense, you have the compiler, the editor, and you kind of go between them. But programming systems like Smalltalk are environments where you're interacting more directly with the language, and maybe that language then has synthesis agents that can interact with you and write the program together, and they let you then explore the computation more easily. Another problem, which of course is a, a long-running problem in software engineering, is kind of overcommitment to details, but I think it can be particular difficulty in climate modeling. You've committed to some particular implementation details around the structure of how you're actually going to do this computation. You bring in that accidental complexity of the real world execution of the program and how it's going to be parallelized and distributed and so on. And then if you want to change that, well, then it's a huge amount of effort. And there's a lot of work at the moment going into porting climate models to run on GPUs, and that's a huge amount of effort because the existing implementations are overcommitted to details. So, what language abstractions can we have to avoid this? I've done lots of work in the past on comonads and how they can be used to structure array computations with this idea of like a local computation, this kind of kernel or stencil computation that computes the element of an array based on a local neighborhood of elements in the input array, and the structure of a comonad lifts that to become a global computation, sort of traversing the entire thing. And the nice thing about using the kind of comonadic interface is that you can have parallelized versions that do the parallelization internally, and the programmer doesn't have to see that. You can kind of abstract over the implementation details, write your kernel once, but then have this traversal of how it's actually going to be applied be handled by different instances of the comonad. So I've worked on that in the past. I'm perhaps interested in bringing that stuff back in again and thinking about kind of DSLs based on this idea. Another thing, of course, then is about being able to do compilation to different targets, not just different parallelization strategies, but CPU, GPU, and so on. Many languages these days, so that Python and Python JAX, for example, are based on the idea of using overloading to reinterpret things for different pieces of hardware. And there's some more recent sort of DSLs coming out about this. So, for example, GridTools for Python is this DSL, embedded DSL that leverages features of Python to let you have high performance stencil computations. So great to see this kind of work going on, and I think we could do more and have PL research involved in this kind of activity as well. Another nice thing about doing overloading is then you can use that for other kinds of reinterpretation, for example, in machine learning where we want to do automatic differentiation. And languages like Julia, which is becoming popular and starting to be used by climate science as well, uses dynamic multiple dispatch, which lets it do lots of overloading. And so you can write these nice little short programs that then can be overloaded in their numerics, and you can use that for automatic differentiation and then put that into machine learning pipelines and so on quite nicely. But there are sometimes things about the multiple dispatch that make it a little bit tricky, and Julia does let you do this kind of typing thing where you can declare the types and leverage those in some way in the compilation. But because of the multiple dispatch, there's no parametric function type. So if you're trying to bring, higher order combinator patterns to Julia and do, for example, the map function over vectors or lists, you can't actually describe its type in the way that we would in a functional language like OCaml or Haskell or F# or even in Java or even in Python with the MyPy typing, because we can't describe a function from a higher order function input, a function as an input. We can't parameterize over its type and say, oh, it's a function from some A to some B. Instead, we have to write something that's kind of lost some of that detail. So perhaps there's some work that could be done there to bring in parametric function types into Julia and actually kind of increase the expressivity of this language and bring in other ideas based on being able to do that kind of typing. Okay, so I've chucked up a bunch of stuff here, but it's not the only things I'm interested in this space or that would be appropriate for this job. So perhaps you're thinking, oh, this sounds interesting, and you'd be interested in applying. So the position is a research associate position. It's just short of 3 years, 33 months with me at Kent. There's a QR code here which will take you to the job ad. The job posting closes on September 9th, so there's still a few more weeks at this point. And kind of potential topics I'm thinking about are some of the things I've discussed here. Static analysis tools for numerical models, verification of perhaps critical libraries used by scientists, novel language ideas for future computational models, extending existing languages with novel features to support science, and developing new tools to support climate scientists. So where would this job be? So it's based at the University of Kent, which is in Canterbury, which is sort of right down in the corner of England. It's closer to France than it is to London, but it's very close to London, less than an hour on the train, so it's easy to get to other places. We've got this beautiful campus kind of nestled in the countryside at the edge of the city, so it's about 25-minute walk down the hill to the city and the train station, but we're kind of perched on the hill overlooking the cathedral, which you can see there, but surrounded by greenery. And so this is a kind of walk up to the School of Computing here, where the job will be based, over in the corner there, nice nestled into the woods on campus there. And here's the School of Computing building. So if you're finishing a PhD or just finished a PhD in computer science or something similar, and this sounds interesting, then do consider applying. If you've got any queries, please email me here, and do check out more details of the job ad via this QR code and the link in the comment. All right, thanks very much.